Okay, so let's see now if we can really apply the correspondence principle to electricity and magnetism. Now, to do that, we have to review, right? So we're going to recap some classic electromagnetic theory. Particularly, I want to think about what it tells us about photons. So in particular, we're going to be thinking about electromagnetic theory in the context of a traveling wave, right? Or a traveling electromagnetic pulse, right? A little bundle of electromagnetic energy that we might, send traveling along through space. Kind of like those, energy weapons you see in Star Wars. It's like a burst of light that then you see, travel across. I mean, it's not realistic, but that's kind of the idea. I want to think about what classical physics tells us about such a bundle or a pulse of electromagnetic energy, and then I want to think about what kind of constraints that puts on our quantum theory, in particular, whether or not it tells us something about momentum and the photon. So here's a little recap of basic electromagnetic facts. First, you might recall, and it's a really neat thing about electromagnetic theory, that electromagnetic fields can actually store energy in completely empty space. And there's a formula that I hope is familiar to most of you for that. I write down the energy density. I like to call that lowercase u, which would be, because it's a density, I use lowercase, which would be the total energy U, so I use the capital for the total energy, per unit volume in some region. And there's a nice result for that. It's epsilon naught over 2 times the square of the electric field plus 1 over 2 mu naught times the square of the magnetic field. Now, to go along with that, this energy not only can be stored in empty space, it can travel through empty space. So there's a handy vector called the pointing vector. This vector actually tells you how the transport rate of energy. It tells you how much energy per unit time, per unit area is being carried through the field. And that has a rather simple expression. It's 1 over mu naught times the electric field cross the magnetic field. Now here's something that might be a little less familiar to you. If it's not familiar, that's okay. This is pretty much the biggest amount of electromagnetic theory that will come up in our course, and I understand this one's a little bit further out there, but it's still an interesting result, and it's going to be very important for us. Now, as you can send a pulse of electromagnetic field that will then, of course, transport energy across when you hit some kind of a target. But we also know you could send, say, a radio wave over to some particles, and it will exert a force on those particles and transfer momentum to those particles. So you can indeed store momentum in empty space. And there's a nice expression for the momentum density. Again, lowercase letter for the density, which I define as the total momentum in a given volume of space stored in the electromagnetic field, divided by that volume. And the expression for this is very similar actually to the pointing vector. It's epsilon naught times E cross B. And again, if you haven't seen that before, don't worry. We work very hard to make this course as self-contained as possible. Okay, now, these are completely general results. Oh, by the way, if you want to know where this kind of result comes from, basically you follow exactly the same logic that was used to derive the energy density and the energy flow. You follow that same type of logic, you can come to this conclusion. Now, as I was saying, though, these are completely general results. I also wanted to focus on traveling waves, and traveling waves have some extra special conditions. For instance, so for when we're traveling, for traveling wave or pulse, we know something, for instance, about the speed of the pulse, right? That's the speed of light, and c squared is 1 over mu naught epsilon naught. We also know something about the polarization state of the fields. We know how they are related to each other. We know, for example, that the magnitude of the magnetic field is pretty small, right? It's 1 over c times the magnitude of the electric field. We know even more, though. We know something about the direction of the magnetic field. The magnetic field is always perfectly perpendicular to the electric field. And we also know that if we take E cross B, right, that will point in the direction, that'll be proportional to a certain direction, n hat, and that n hat is actually the direction of travel of the wave. Okay, so let's put all of this information together then to see what we can learn about energy and momentum in classical physics in the electromagnetic field. In particular, the first thing we would do, actually that will help us a little bit, is to simplify this expression for the energy density. And then we can relate it to the momentum. So let's start with the simpler thing. Energy is always simpler. It's a scalar. So U, as we know, is epsilon naught over 2e squared, right? Plus 1 over 2 mu naught times b squared. But now we can use the fact that the magnitude of the electric field is exactly the magnitude of the electric field divided by c. So basically I'm going to be substituting this result in for b. And when I do that, I'll get e squared on top and c squared on the bottom. So there'll be an e squared up here and an extra c squared down here. But now look at this. This is kind of neat. This combination, notice 1 over mu naught c squared, you can see, has a very special value because I could take this c squared, I could put it into my denominator, which would give me 1 over mu naught c squared, and I can see then that will equal, I can get what it equals by moving this epsilon naught to the other side of my equation where it shows up on top. So this combination is actually equal to epsilon naught. But then I've got epsilon naught on 2 e squared. It's exactly the same as the first term. I have two equal terms, which then just doubles the result, which then kills my 1/2. So the final result, in terms of just the electric field, simplified down for special case for traveling waves, it's just epsilon naught e squared. Beautiful. Now, let's look at that momentum density. It's kind of a new quantity for us. Momentum density is epsilon naught. Again, I've got my epsilon naught constant. Now I have to do E cross B, which has a magnitude and direction. The magnitude of the cross product, you know, is the product of the two vectors, E times B, times the sine of the angle between them. But fortunately, we know that E and B are always perpendicular, so we know that angle is 90 degrees. This gives me the magnitude of the cross product. I also need the direction, but I happen to know that E cross B is exactly in the direction of travel. So the direction then would be this travel direction n hat. Now we can simplify, right? Sine of theta, sine of 90, that's easy. That's just 1. So that goes away. For B here, I know once again the magnitude of that is just E over C, which I can substitute in for B. So what I'm left with then is I've got epsilon naught E, when I substitute this in, I've got E squared on top and C on the bottom. So I've got epsilon naught E squared. Oh, that's interesting. That's my energy density. Divided by, remember I'm substituting E over C, so divided by C. And the direction of the momentum stored is just in the direction of travel of the wave, which makes sense. My wave's going this way. It makes sense that it'd be carrying momentum in that direction. So our final result then is that the momentum density in the electromagnetic field is equal to, this is my energy density, U over C, and it points in the direction of travel. Very interesting result. Next thing I can do with this, right? Now that I have this, I can integrate both sides of my equation over the both sides, right? So each side I will integrate over the volume, say, of my pulse. And when I do that, when I integrate the momentum density over the volume of my pulse, of course, that just gives me the total momentum of my pulse. So the total momentum of my pulse will equal. When I integrate the right-hand side, the direction of travel is constant. C is constant. So I have these two constants I can pull out. So there will be an n hat over C. And then what I'm left with is the integral over the energy density, which of course has to give me the total energy in my pulse. That's what I've been calling capital U. I'm going to call it E here for energy just because that's the way people usually write the formula we are about to derive. So The total momentum vector is just the total energy in the pulse over c times the direction of travel. Usually people, because it's pretty clear momentum should be in the direction of travel of the pulse, usually people just worry about the magnitude. If I take the magnitude of this equation, what I get is that the total momentum magnitude P equals the total energy E divided by C. Or the other way people like to write this for electromagnetic pulses is that the total energy stored is just C times the total momentum stored. Either way that you like your result, this is sort of our key conclusion. Okay, that's the result of classical physics. And we have to stay consistent with this. But we also know that this energy is delivered out of our pulse in discrete units, these photons. So what I want you to imagine is, say I've got this electromagnetic pulse here, right? And he's traveling through space, right? And say he's about to travel over some location where maybe, I don't know, there might be a bunch of electrons. And as it's traveling over these electrons, right, that's when it can start delivering these energy packets. And as it begins to deliver these energy packets and its energy decreases, according to this formula here, if the energy decreases, the momentum has to decrease. And it has to decrease just in the amount given by this formula. So it seems that when I'm delivering my energy packets to the electrons, if I'm losing momentum out of my pulse, it must be going somewhere. I believe in conservation of momentum. It must be also being transferred to my electrons. So in each of these energy packet deliveries, there's also a momentum that seems to be delivered, and the amount of that momentum seems to be just proportional to the amount of energy transferred. So what we can say then is we think, this is going to be our guess, right, or our hypothesis, if you want to be formal about it, right, our hypothesis is going to be that, in fact, the for a photon, it must be carrying a momentum p that occurs in these discrete units, right? And in order to keep this proportion, the simplest guess would be that every photon delivers the same amount of momentum, right, corresponding exactly to the discrete change in the energy that occurred. So the energy transferred in each individual photon we know is h nu from the photoelectric effect. And if we want to keep the same proportion, which we know macroscopically, if I deliver a lot of these energy packets, I have to lose exactly the total energy that I lost from them divided by c. It's very reasonable to assume that every individual packet obeys that rule. So for photons, we're going to assume that there is a discrete momentum packet as well that comes in this particular amount. Now, I should say, and we want to keep in mind, that strictly speaking from the correspondence principle, all that we really know is what happens when we deliver a large number of packets. So really all that we know, strictly speaking, is that the average momentum delivered in each photon packet would have to have this value. Right? We don't know what's going on with the individual ones, but the way we do our science is we make the simplest possible hypothesis consistent with our new data, and we test it. And if it works, you've got your Nobel Prize. If it doesn't work, well, then, you go back to the drawing board. So this now is a hypothesis that we have out there, and we now need to test it.